So here's our game plan. We're going to follow the exact same logical path a structural engineer would. We'll start by figuring out what the actual problem is, then we'll size the footing, run some absolutely critical safety checks for shear, analyze all the internal forces at play, and finally design the rebar that holds the whole thing together. Let's get into it. Okay, so first things first, why are we even doing this? Why a combined footing? Understanding the why behind it is really the key to appreciating the entire design we're about to walk through. And here it is, the root of the problem. You see column A? It's sitting right on the property line. That means we literally cannot extend its foundation outward. So the only safe and stable way to support it is to join forces, combining its footing with the one for the nearby column B. Every single design has to start with a set of givens. These are our non-negotiables. We know how much pressure the soil can safely handle, we know the strength of our concrete and steel, and we know the service loads, which you can think of as the everyday expected forces for each column. These numbers right here, they're the bedrock for every single calculation we're about to make. Okay, with our parameters locked in, it's time for our first big move, figuring out the actual physical size of this footing. We've got to calculate the length, the width, and the thickness that we'll need to safely carry the loads from both of those columns. Now, this is absolutely the most critical idea in this step. We have to get uniform soil pressure. The goal is for the ground to push up evenly everywhere. To make that happen, the dead center of our footing has to line up perfectly with the combined center of the column loads. By finding this resultant force location, X, we can lay out the footing so it won't tilt or settle unevenly, which would be, well, very bad news. The sizing process is really systematic. First, we use those daily service loads to figure out the area we need so we don't overstress the soil. Simple enough. But then, to design the strength of the concrete footing itself, we have to ramp things up. We apply safety factors to get the ultimate load. This gives us the ultimate soil pressure, and we use that to make sure the footing won't physically fail or break under a worst-case scenario. So we've got the dimensions. Are we done? Not even close. Now we have to prove that our footing is thick enough. And this is all about preventing failure, starting with a critical force called shear. Just imagine trying to push a nail through a piece of cardboard. If that cardboard isn't thick or strong enough, the nail just punches right through. Well, punching shear is the exact same idea, but with a massive column on a concrete slab. Our job is to make sure our concrete is strong enough to stop that column from just punching a hole through it. Now, what's really interesting is that to check for punching shear, we don't just look right at the face of the column. The design codes tell us to check at a critical perimeter, a specific distance away from it. Why? Because that's where this kind of failure would actually start. That's the zone we have to watch. And here are the results of our checks. For both columns, you can see the demand, that ultimate shear force, is way less than the shear capacity of the concrete. This confirms it. Our chosen footing thickness is more than enough to prevent a punching shear failure. So, check. We're good to go. Okay, we've confirmed the footing is thick enough. Now we need to figure out how much steel reinforcement it needs. To do that, we have to analyze it as if it's a giant upside-down beam. This helps us see all the internal forces that are at play inside the concrete. This slide right here, this is the heart of our entire analysis. These two diagrams, for shear force and bending moment, are like a map of the internal stresses all along the footing's length. Those peaks and valleys, they tell us exactly where the stresses are highest, and that tells us exactly where we're going to need the most steel. Out of all the numbers on those diagrams, one is the star of the show, negative 1,366 kilonewton meters. This is our peak bending moment. And that little negative sign is so important. It tells us the footing is trying to bend upwards between the two columns. That means the top surface is being stretched, it's in tension. And this one value is going to drive our main steel design. So along with those bending forces, our diagrams also pointed out the maximum shear forces. So we do one last check for what's called beam shear at that critical point. And just like with punching shear, the capacity is greater than the demand. So once again, our design is safe. All right, the analysis is officially done. Now it's time for the final, most practical step, translating all those forces and moments into an actual design of steel reinforcing bars, what we all call rebar. So we take those peak bending moments we found, and we plug them right into these standard design formulas. What these equations do is basically convert a force, the moment, into a physical thing, the area of steel we need to resist all that tension we were talking about. And here's what the math spits out. To handle that huge negative moment happening between the columns, we need a good amount of steel up near the top surface. The solution? 9 20mm bars for every meter of width. Then, in the other spots where the moment is positive, we just need a smaller, minimum amount of steel at the bottom. Now, of course, we can't forget that the footing also bends in the short, or transverse, direction. So a few similar calculations tell us the steel we need there. And with all the pieces finally calculated, we can bring them all together into one final, comprehensive reinforcement drawing. And this is it. This is the final product. This drawing is the ultimate goal. It's the instruction manual for the construction crew on site. It clearly shows the size, the spacing, and the location of every single piece of rebar. It's where all our analysis and calculations become reality.